Number 10. WASP-12b egg-shaped tidal distortion into host star. WASP-12b is located roughly 1,200 light-years away in the constellation Auriga, and its discovery was announced on April 1, 2008. The planet experiences strong tidal interactions with its host star due to its extremely close orbit, resulting in synchronous rotation where the planet's spin period matches its orbital period of approximately 1.09 days. Gravity causes enormous tidal forces which are stretching the planet into the shape of an egg, creating a distinctive prolate distortion. These forces elongate the planet into a prolate, egg-like form with the long axis pointing toward the star, deviating from sphericity and altering its observed transit light curve by about 10%. The planet is so close to WASP-12 that the star's tidal forces are distorting it into an egg shape and pulling away its atmosphere at a rate of about 10 to 7 mJ per year. Modeling of ground-based transit light curves provided evidence of tidal distortion, supporting a prolate planetary shape with the light curve deviating by approximately 10% from a spherical model, and confirming strong tidal interactions. Analysis of transit time spanning over a decade reveals a decreasing orbital period at a rate of -29 ± 2 milliseconds per year, providing the first robust evidence of inspiral in an exoplanetary system. Researchers confirmed WASP-12b's orbit decay, indicating that it will be consumed by its star in just 3 million years as the planet spirals inward. The physics governing the rapid rate of tidal dissipation in the system continues to be studied by astronomers seeking to understand extreme star-planet interactions. Number 9. HD 1893-30b sideways, glass rain 7,000 km winds. HD 1890-733 is a gas giant exoplanet located 63 light-years from Earth in the constellation Vulpecula, with atmospheric temperatures exceeding 1,000 degrees Celsius and winds that howl at 7,000 kilometers per hour. The planet's deep blue color comes not from water oceans, but from silicate particles suspended in its upper atmosphere that scatter blue light more effectively than other wavelengths. This hot Jupiter orbits extremely close to its parent star, HD 189733, completing one full orbit every 2.2 days. More than 30 times closer than Earth is to the Sun. Scientists believe the precipitation on this world consists of particles of enstatite and forsterite, common silicate minerals that form the raw materials of glass. The dayside heat is intense enough to vaporize glass, and winds reaching 5,000 miles per hour blow this glass vapor to the cooler night side where it condenses and falls sideways at high speeds. Astronomers using the James Webb Space Telescope detected trace amounts of hydrogen sulfide in the planet's atmosphere, a toxic molecule that smells like rotten eggs. The detection of silicon dioxide grains in HD 1893-30b's dayside emission spectrum provides the first direct confirmation of silicate particles in this planet's atmosphere. The winds on HD 1893-30b blow at up to 5,400 miles per hour, approximately 7 times the speed of sound. Astronomers in France discovered the planet on October 5, 2005, by observing its transit across the face of its host star. Number 8T RES 2b coal black albedo, less than 1%. TRES-2b is a Jupiter-sized gas giant orbiting a yellow sun-like star designated GSC 0354928, 1-1, located approximately 750 light-years away in the direction of the constellation Draco. Astronomers determined that this exoplanet reflects less than 1% of the sunlight falling on it, with the best fit model estimating an albedo of about 0.04%. This extremely low reflectivity makes TRES-2b darker than coal or black acrylic paint, and blacker than any planet or moon in our solar system. David Kipping, an astronomer at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, described the planet as appearing like a near-black ball of gas with a slight glowing red tinge. Using NASA's Kepler spacecraft with observations of over 50 orbits, Kipping detected the smallest ever change in brightness from an exoplanet at just 6 parts per million, allowing direct detection of visible light coming from the planet itself. The planet orbits its star at a distance of only 5 million kilometers, where the star's intense light heats TRES-2b to temperatures exceeding 1000 degrees Celsius. The extreme heat prevents reflective ammonia clouds from forming, and the atmosphere instead contains light-absorbing chemicals like vaporized sodium and potassium or gaseous titanium oxide. Yet none of these chemicals fully explain the extreme blackness of TRES-2b, and co-author David Spiegel of Princeton University stated it is not clear what is responsible for making this planet so extraordinarily dark. The underlying cause of the planet's record-breaking darkness remains unresolved, and researchers continue to investigate what mechanisms could produce such an exceptionally low albedo. Number 7. PSRB1257 plus 12. System pulsar planets bathed in radiation. PSRB1257 plus 12 is a millisecond pulsar located 2,300 light-years from the Sun in the constellation Virgo, rotating at 160.8 times per second. The pulsar hosts 3 known planets named Draugr, Poltergeist, and Phobator, which were the first extrasolar planets ever discovered, with the 2 larger planets found in 1992 and the smallest in 1994. The planets range in mass from 0.02 to 4.3 times that of Earth, and orbit between 28 and 69 million kilometers from the pulsar. The pulsar planet system was discovered by Alexander Voltsan in 1992 using the Arecibo radio telescope in Puerto Rico. Pulsar planets like Poltergeist and its neighboring worlds are consumed with constant radiation from the star's core. The Chandra X-ray Observatory detected the millisecond pulsar B1257 plus 12 in a 20 kilosecond exposure, finding 25 photons with energies between 0.4 and 2.0 kiloelectron volts. Researchers calculated that pulsar planets could survive their hosts' violent outbursts if they are equipped with atmospheres about 1 million times as thick as Earth's. Scientists face difficulties explaining how the observed planets could have survived the supernova explosion responsible for the neutron star, leading to the conventional belief that the planets must have formed after the supernova. The physics governing planetary formation around pulsars remains an area of active research, with several competing theories proposed but no consensus reached on the exact mechanism. Number 6. KELT9b hottest exoplanet molecular hydrogen dissociation. KELT9b is an ultra-hot Jupiter located about 670 light-years from Earth, approximately 3 times the mass of Jupiter. The discovery of KELT9b was announced in 2016, detected using the kilodegree Extremely Little Telescope. It is the hottest known exoplanet with dayside temperatures approaching 4,600 K, warmer than some K-type stars. On the dayside, molecules are broken into their component atoms, so that elements like neutral oxygen, neutral and singly ionized atomic iron, and singly ionized titanium can exist as atomic species. Astronomers using NASA's Spitzer Space Telescope presented a phase curve of KELT9b observed at 4.5 micrometers to study the impact of molecular hydrogen dissociation. The best fit for the data was a model that included hydrogen molecules being torn apart and reassembled, a process known as dissociation and recombination. These atoms temporarily reform once they reach the cooler night side, with enhanced heat transfer efficiency of 0.3 between dayside and night side, likely driven by the latent heat of dissociation and recombination of molecular hydrogen. The planet has a dayside brightness temperature of about 4,566,000 and a nightside temperature of about 2,556 K. Surprisingly, spectra taken in 2021 indicated a presence of metal oxides and hydrides in the planetary atmosphere, although higher resolution spectra have not found molecular emissions from the planetary dayside. Number 5. 55 Cancri E diamond planet carbon-rich composition. The planet 55 Cancri E is a super-Earth orbiting a Sun-like star located 40 light-years from Earth in the constellation of Cancer, and has around twice the diameter of Earth and roughly 8 times its mass. The planet orbits at hyperspeed, with a year lasting just 18 hours, making it one of the most extreme worlds known to science. A team led by Niku Madhusudan at Yale University suggested that the mass and diameter measurements would make sense if 55 Cancri consists mainly of carbon. supported by spectroscopy measurements indicating that the planet's host star is carbon-rich. Models revealed that 55 Cancri E could possess an iron core surrounded by a mantle of silicon carbide and covered with a thick crust of graphite and diamond that may account for around a third of its mass. Research suggested the planet has no water at all and appears to be composed primarily of carbon as graphite and diamond, iron, silicon carbide, and possibly some silicates, with at least a third of the planet's mass potentially being diamond. However, a later study showed that planet 55 Cancri E is less likely to consist largely of diamond, revealing that the carbon-to-oxygen ratio appears to be lower than previously thought in the planet's host star. Recent JWST observations of 55 Cancri E provide some of the best evidence to date of an atmosphere surrounding a rocky exoplanet. Though JWST observations have ruled out the rock vapor atmosphere scenario and provided evidence for a substantial atmosphere rich in carbon dioxide, or carbon monoxide, the origins of the extreme emission variability remain poorly understood, and there is significant degeneracy between the predicted composition and the properties of the possible atmosphere of 55 Cancri E. The question of whether 55 Cancri E is truly a diamond world remains unresolved as scientists continue to refine models of its interior composition and atmospheric chemistry using new observations. Number 4. J1407b, Super Saturn Ring System, 200 times larger. Dr. Matthew Kenworthy of Leiden Observatory and Professor Eric Mamajek of the University of Rochester discovered the object J1407b, which orbits the young star J1407 located approximately 434 light-years from Earth. The host star J1407 is a 16 million-year-old pre-main sequence star, far younger than our own Sun. The ring system surrounding J1407b is roughly 200 times larger than Saturn's rings are today. Analysis of the star's dimming suggests that J1407b's disk has a radius of 0.6 astronomical units, or approximately 90 million kilometers. The ring system consists of about 37 rings, each of them tens of millions of kilometers in diameter. Gaps found in the rings indicate that exomoons may have formed within the system. The mass of J1407b is estimated to be in the range of about 10 to 40 Jupiter masses. The star is much too far away to observe the rings directly, but researchers created a detailed model based on rapid brightness variations in the starlight passing through the ring system. The exact nature of J1407b remains debated, as some analyses suggest it may be an isolated substellar object rather than a planet gravitationally bound to its host star. Number 3. WASP-103b Rugby Ball-Shaped Tidal Deformation. CHEOPS. The CHEOPS Space Telescope detected the first ever observation of tidal deformation in an exoplanet, revealing that WASP-103b has been stretched into a rugby ball shape. WASP-103b is located in the constellation Hercules and is almost twice the size of Jupiter, with 1.5 times its mass. The planet orbits its host star, WASP-103, in less than 1 day. About 50 times closer than Earth orbits the Sun, the host star WASP-103 is approximately 200 degrees hotter and 1.7 times larger than the Sun. CHEOPS is a joint mission of the European Space Agency and Switzerland, led by the University of Bern in collaboration with the University of Geneva. Researchers from the universities of Bern and Geneva and the National Center of Competence in Research Planets published their findings in the journal Astronomy and Astrophysics. Babatunde Akinsanmi, a researcher at the University of Geneva, noted that this was the first time such an analysis of tidal deformation had been accomplished. The detection was made possible by combining CHEOPS observations with previous data from the Hubble Space Telescope and Spitzer Space Telescope. Future observations with CHEOPS and the James Webb Space Telescope will be needed to further understand the internal structure and tidal deformation of WASP-103b. Number 2. Kepler-16b Circumbinary Planet Orbiting Two Suns. Kepler-16b is the first planet known to definitively orbit two stars, a configuration that astronomers call a circumbinary planet. NASA's Kepler mission made the first unambiguous detection of this world about 200 light-years from Earth, though some sources place it at 245 light-years away. The planet is a Saturn-mass exoplanet consisting of half gas and half rock and ice, and it is cold and not thought to harbor life. Kepler-16b orbits its binary star system with a period of 229 days, circling both stars rather than just one. The planet transits each star, and Kepler data from these planetary transits allow the size, density, and mass of the planet to be extremely well determined. The orbits of the stars and the planet align within a degree of each other, indicating that the planet formed within the same circumbinary disk that the stars formed within. While the Kepler Space Telescope originally found Kepler-16b using the transit method, astronomers later found it independently using the radial velocity method. Dr. Alexandre Sainterne from the University of Marseille was among the researchers who used ground-based telescopes to confirm the planet's existence through this alternative detection technique. The discovery demonstrated that circumbinary planets are real, and that planetary systems can form and remain stable in environments very different from our own solar system. Number 1. Gliese 1312b secondary atmosphere regeneration after stripping. Gliese 1312b is a rocky exoplanet located 41 light-years away, orbiting a red dwarf star in the constellation Vela. The planet is hypothesized to have begun as a gaseous sub-Neptune with a thick hydrogen blanket of atmosphere, starting out at several times the diameter of Earth. This primordial hydrogen and helium atmosphere was quickly stripped away due to intense radiation from the hot young star it orbits. In a short period of time, the planet was reduced to a bare core about the size of Earth. Mark Swain of JPL, the lead author of the study, explained that this atmospheric stripping process works early in a planet's life when the star is hotter. Hubble Space Telescope observations revealed a secondary atmosphere rich in hydrogen, hydrogen cyanide, methane, and ammonia, with a hydrocarbon haze. Astronomers theorized that hydrogen from the original atmosphere was absorbed into the planet's molten magma mantle and is now being slowly released by volcanism. Recent JWST observations combining transmission and emission data show results consistent with only the thinnest of atmospheres, leading researchers to conclude that the simplest explanation is a bare rock. The case of Gliese 1032b has raised important questions about whether secondary atmospheres can remain stable on rocky exoplanets orbiting close to active stars, a process that scientists continue to investigate.